Everyone, my name is Marko Dragojevic and I'm coming from the RTRK Research Institute, and today I will present you a paper called Advanced Lane Finding Prototype based on Autoware platform. So basically, automotive industry has been on a rise in recent years and led to see rapid expansion. Prior to introduction of more powerful in-car computer platforms, which are capable of providing more processing power, there were multiple ECUs scattered all around the vehicle, and they were mainly focused on providing some kind of minimalistic functionalities and safety rather than providing a considerable amount of processing power. Main or most notable, or even I would say main goal of modern automotive industry is producing a fully autonomous vehicle. Autonomous vehicles, of course, need to have a set of different sophisticated sensors, such as cameras, lidars, radars, ultrasonic sensors, etc. And all this sensor data has to be fused together in order for vehicle to be able to perceive its surroundings. And complex software algorithms come into play here. So functionality of autonomous vehicles must be properly tested before start of mass production, and performing live tests on autonomous vehicles come with a great risk of potential injuries or even fatal cases, and that's why in automotive industry different approaches for testing are mostly preferred, such as mill, seal, or hill tests. So that's model-in loop, software loop, and hardware loop testing techniques. And application prototype, which is shown, is described in this paper, was seal tested in order to get some early feasibility check on its functionality. There are a few main goals on this paper, and the first one is to emphasize importance and benefits of early software prototyping. The second one is to actually develop a perception application prototype in a ROS environment, and third one was to get some early feasibility check for future application, which will be part of Adaptive AUTOSAR platform as a reactive control component, and it's very important for it to have short sense-act plan loop, which could serve as an lane information provided to a higher level applications such as localization applications or perception applications. And another use case of this application could be to actually use output to directly control vehicle steering angle in order to keep car from drifting away from the center of the lane, for example in a highway scenario. And early testing and integration strategy was also set up in this process of developing application prototype. First, let's have an overview of prototyping platform, which was mentioned earlier, and its name is ROS. So ROS stands for Robot Operating System, and it's actually a framework, or some even say meta operating system, for developing robot-based applications. It's an open source software with a really big community and a really big community support. Modular and distributed applications are possible to build with on top of this robot operating system, and ROS is actually a base for many advanced platforms such as Autoware. And the main pro about ROS is its flexible communication interfaces and rich utility toolset, where we have different tools for visualization, simulation, etc. So second platform we will mention here is the Autoware platform, and it's actually based on ROS, and it is a fully functional autonomous driving platform which has already been field tested, and it comes with a set of already implemented functionalities, which is very important for rapid prototyping, because we do not have to focus on developing surrounding functionalities. Instead we can focus on actually implementing and testing our own implementation or our own piece of software. Autoware platform can roughly be abstracted into three modules. The first module is called sensing module, second one is computing, and third one is actuation module. So sensing module handles interaction with sensors such as cameras, lidars, inertial sensors, GPS, etc. The actuation module handles the actual vehicle control, lateral and longitudinal vehicle controls, and computing part or computing module is the actual brain of Autoware platform, and here we have perception algorithms, localization, detection, prediction, different kind of prediction algorithms are running. We have a state decision or state transition functionalities here, and also we have mission and motion planning, trajectory planning, etc. This platform is really modular, really extensible, and that's why it's a great prototyping platform. And additional pro to using this platform is it is actually really similar to adaptive AUTOSAR platform, which will be mentioned in following slides, because it supports similar communication patterns as this platform. So, target platform, yeah, on which the final application will run is the adaptive AUTOSAR platform. So, alongside already known and field-proven AUTOSAR classic platform, new platform is also introduced in recent years, and it's called adaptive platform. Adaptive platform will potentiate realization of functionalities related to autonomous driving, and which includes, for example, complex algorithms for object detection or sensor fusion. Main goal of adaptive AUTOSAR platform is to provide a uniform runtime environment for different kind of adaptive applications, and this is really similar to the interface ROS and Autoware platforms provide for their applications. And also another similarity with ROS and Autoware platform is that both architectures are actually service-oriented, and both architectures also support direct client-server communication. Adaptive AUTOSAR is an actually open standard, which is made by AUTOSAR consortium, but although standard is open, the actual implementation is almost always proprietary, OEM specific. Oftentimes, platform is not available from the start, so prototyping has to take place in order to continue with development of applications that will run on top of this platform, and this is the case in this paper also. And that's why we are using other prototyping platforms until we have final adaptive platform available. On this slide, general architecture of our solution of our prototype application is shown. As it can be seen here, application actually consists of processing pipeline and some additional abstraction layers in order to help us reduce coupling between application and the platform itself, and to make migration from one platform to another platform cheap, fast, and easy. So basically, COM adapter is this abstraction layer, and it's used to actually hide platform-specific communication mechanisms and provide the needed input and means for outputting the result from our application logic. And this information that our application is sending to the rest of the system could actually be used in order to provide additional lane information to some other, for example, camera or lidar-based applications, or even try to manipulate or even to say better, directly manipulate vehicles lateral and longitudinal controls in order to keep vehicle on the center of the current lane and to avoid vehicle drift out from the current center of the lane. The second part of our solution is the actual processing pipeline, and then it actually consists of a few steps. So first step is to actually correct the distortion of the image. Second step is to apply binary thresholding techniques in order to extract potential edges that will later be decided if they are actual lane lines or not. After that, perspective transformation from the frontal camera view mounted on the center of a vehicle is moved to the bird view perspective, where we can see and extract position of lane lines more efficiently. After that, we search for lane lines in a current frame. If no detection is present from previous frame, we of course do a blind search. Using sliding window approach, we know estimated position in a current frame where lane lines should be, and we start our search from there. After we have detected start of the lane line, we then follow that line with our sliding windows, and all the pixels that belong to the lane line are actually marked uh, and with this we indicate that they belong to the current line. If we have information about position of the line from previous frame, we do highly targeted search, and we actually just search around the area where the line was in a previous frame. And we also mark these pixels as a belonging to the lane line. In the end, second degree polynomial is fitted through all these marked pixels, and this is our representation of lane lines. And from here, we have information about lane lines. Next step is to actually calculate, with this information, we can actually calculate vehicles offset from the center of the lane, or even lane curvature radius. Also, information about lane position within a frame could be useful for some other camera-based applications, and it could serve as available output in order, for example, to reduce region of interest. If we have, for example, some object detection algorithm, vision-based algorithm, we can actually reduce the area where that algorithm needs to perform search for his objects. And in the end, this can be seen on the last image down here, on the down left side of the slide, is the inverse perspective transformation, where we return to the original position of a camera, and we use our information acquired about lane lines position in order to plot or to display this acquired information on our frame. So as for solution validation, prototype has been tested against simulated data, and we have used the Light Scala simulator in combination with Autoware platform. So our solution or our prototype has been tested against simulated data. But in addition to this, also our application has high level of test coverage on all levels, unit, integration, and acceptance level tests. Also, TDD or test-driven development methodology was used while developing this prototype, which ensures greater product or code quality. And as a result of all this, we have testing and integration strategy already in setup. So once our platform is available, migration from one platform or Autoware or our current platform to our target platform or adaptive platform will be much more easier, much less time consuming, and much cheaper. So our main concern regarding this prototype application performance was if it was going to be able to achieve somewhat fast execution time, since reactive control components have to have short duration of sense, plan, act loop. And current preliminary results shows that execution took around 31 milliseconds per frame on high-end laptop and around 21 milliseconds per frame on specialized embedded NVIDIA Drive PX2 platform. And the difference is the difference in execution time originates from the fact that Autoware platform is supported and optimized by Drive PX hardware platform, and it uses hardware support appropriately. Of course, these are only preliminary results, and this is also one available input for us to continue development of our prototype application. And these preliminary results on embedded hardware platform will serve as a input for redesigning, potential redesigns or potential reorganization, refactorization of our and final target application. In the end, let us conclude this paper. So in this paper, we have shown that open source prototyping platforms such as Autoware can be actually used to develop automotive grade applications, or to be more precise, prototypes for automotive grade applications. With utilizing Autoware, we were granted the chance of really feasibility check of our application, thus reducing chance of interesting flaws in design of our applications, which could potentially be very expensive and hard to mend in later stages of application development, or to say if they emerge in later stages. And we have also established a good base for development of our actual adaptive application. We have also set up integration and testing strategy. and this provides additional mean to actually decrease the final application time, time to market, and cost of the final application. What else can I say? Also, yeah, with this application prototype, we had a chance to get some initial measurements on a real embedded hardware, and this also serves, as I already mentioned on a previous slide, it also serves as a valuable input for us in order to uh, fix potential shortcomings of our application. And in the end, to answer the question I received actually two questions regarding this paper. The first one was, what is the relation between AUTOSAR and AUTOSAR platform? I'm sorry, what is the relation between Autoware and AUTOSAR platform when it comes to final solution applicability? Well, the main relation between Autoware and adaptive platform are, as I mentioned, their similarities in architecture and similar use cases they support. Both platforms are based for high performance algorithms which represent core functionality of autonomous vehicles. In addition to this, similar communication patterns are used in both platforms. They both support service-oriented communication and client-server communication, and that means that our solution design should not really require any changes on platform's web, and this gives us the opportunity to develop solutions to some degree and discover potential flaws. Thus, also gives us the opportunity to actually discover potential improvements, which could increase the final solution's applicability. For example, one such improvement could be pairing our functionality of our application with some other applications, and as a result, increasing the effectiveness of both. I already mentioned something similar when I was explaining about solution of this application. For example, we could combine our application, which provides lines information, to some other, for example, vision-based application, which does, for example, object detection on a road. And with this, we could more efficiently and more precisely reduce the region of interest that other detection algorithm has to search for the objects of interest. And second question, I hope this one is a good answer. And second question was, in my view, lane keeping and distance keeping, can this be actually considered autonomous driving at level 3? Well, my personal opinion about lane keeping and distance keeping is that both functionalities actually fall in level 2 of autonomous driving, and they are already field-proven solutions regarding this topic. And both lane keeping and distance keeping functionalities are already present in commercial vehicles. But lane keeping and distance keeping applications used in a somewhat different scenario, used alongside highway pilot, for example, could actually prove to be at level 3 or even level 4 of autonomous driving. And this application described in this paper is actually aiming to be a integral part of such complex system. I hope my answers were helpful in understanding this paper. Thank you and goodbye.